students, welcome to this lecture. In this lecture we will start our discussion of boundary value problems. So, boundary value problems means equation is given and the conditions are defined on the boundary of the domain. So, let us see what is the boundary value problem in a precise manner. So, consider the second order linear differential equation P naught x y double dash plus P 1 x y dash plus P 2 x y equal to R of x here. So, here coefficients P naught, P 1 and P 2 are continuous in a interval j which is alpha to beta, where alpha beta are any real number in real numbers and alpha is less than beta, we say. Then we assume that function P naught, P 1 and P 2 and R x are continuous in J. So, by existence and uniqueness theorem we simply say that this solution exists if we are prescribed the initial condition along with this. But now let us consider the differential equation with the boundary condition like this. So, here we define boundary condition of the form L 1 y equal to L 1 y, where L 1 y is given as A naught y alpha plus A 1 y dash alpha plus B naught y beta plus B 1 y dash beta, and it is given taken as some value that is A. And second boundary condition is C naught y alpha plus C 1 y dash alpha plus D naught y beta plus D 1 y dash beta equal to B. Here A and beta are again some real constant. So, here A I, B I, C I, D I for I equal to 0 to 1 and A and B are given constant, real constant, and throughout we assume that these two conditions, the previous two conditions are linearly independent. So, we simply say that these are not precisely the same conditions. So, here we are assuming that the vector A naught, A 1, B naught, B 1 are not scalar multiple of C naught, C 1, D naught and D 1. So, it means that these two vectors are linearly independent vectors. So, it means that we are precisely working with two linearly boundary condition rather than one boundary condition. So, here I am assuming that there exists no k for which this is true. So, it means that we are assuming that the condition given in 2 are linearly independent boundary conditions. So, it means that now we define the boundary value problem. So, boundary value problem 1 comma 2 is called a non-homogeneous 2-point linear boundary value problem, whereas the associated homogeneous differential equation together with the homogeneous boundary condition will be called a homogeneous boundary value problem. So, first you just look at here, there is a equation and a boundary condition, because this condition the defined on at 2 point alpha one endpoint and beta is another endpoint. So, we simply say that these L 1 y and L 2 y are conditions defined at two different points, that is alpha and beta. So, we say that L 1 y and L 2 y are boundary condition rather than initial condition, because it is defined at two different points, in fact at the end point of this. So, we call it boundary conditions or 2-point boundary conditions. It may happen that we have some more point on which we may define condition in terms of more points, but right now it is a boundary 2-point boundary value problem. Now, we defined non-homogeneous and non-homogeneous equation and non-homogeneous boundary condition. So, if this R x is non-zero for not 0 in the whole interval, then we say call it non-homogeneous differential equation, and if A and B are non-zero real constant, then we call these boundary conditions are non-homogeneous boundary conditions. So, it means that if we consider non-homogeneous differential equation with non-homogeneous boundary condition, we call this as a non-homogeneous 2-point linear boundary value problem. But if we consider that R x equal to 0 and A equal to 0 equal to B, we call it that this is a homogeneous boundary value problem. So, it means that associated homogeneous differential equation together with the homogeneous boundary condition, that is L 1 y equal to 0 and L 2 y equal to 0 will be called a homogeneous boundary value problem. So, it means that when R x equal to 0, A equal to 0, A equal to B, then in this case we call this as homogeneous boundary value problem. But if R x is non-zero, A and B are all non-zero, then we call it non-homogeneous boundary value problem. Okay. In fact, one of A and B has to be non-zero in non-homogeneous boundary value problem. Now, we define a regular boundary value problem and singular boundary value problem. So, we simply say that boundary value problems 1 and 2 is called regular if both alpha and beta are finite and the coefficient p naught x, coefficient of d2y by dx is square, this p naught x, this is non-zero in the entire interval j. So, if interval is finite and the coefficients are non-zero, then we call our boundary value problem as regular boundary value problem. Otherwise, we call our boundary value problem as singular boundary value problem. It means that if your alpha is minus infinity and or beta and or r beta equal to infinity and or p naught x equal to 0 for at least one point in j, then the problem 1 and 2 is said to be a singular boundary value problem. And for this particular course, we will consider only the regular boundary value problem. It means that we consider that our endpoints are finite and the coefficient of d2y by dx square is never 0 in the said interval, in finite interval. Now, the boundary condition which we have considered L1y equal to A and L2y equal to B are very general boundary conditions, and we can summarize and we can write many more boundary condition as a special case of L1y and L2y. So, first let us take a special case where L1y is given as y alpha equal to A. So, here L1y is y only. So, here L1y which I am writing as here we are simply taking L1y is basically taking only A naught as 1, rest are all 0. So, we say that the simplest form of L1y is that A naught is equal to 1, rest are all simply 0. So, L1y is equal to simply y only. So, here we simply say A naught is equal to 1, so y alpha and all are 0, 0 y dash alpha plus 0 y beta plus 0 y dash beta. So, it is a particular case of your L1y. So, here we simply assume that A naught equal to 1, rest are all 0. Similarly, you assume that C naught is equal to 1, rest are all 0. So, we have boundary condition y alpha equal to A and y beta equal to B. So, we say that it is first boundary condition, and sometimes we call it a Dirichlet condition. So, here in first boundary condition or Dirichlet condition, your function is given some value at the end point, and then second boundary condition which we call as mixed boundary conditions, where function as well as its derivative is defined at the end points. So, here one kind of mixed boundary condition is y alpha is given as A and y dash beta is equal to B. So, it means that at one point your function is given and the other point your derivative is given. So, y alpha equal to A, y dash beta equal to B, or the other way, that is y dash alpha equal to A means at the end of x equal to alpha your derivative is given a particular value and the other end the function is defined or getting a particular value. So, this is your second boundary condition, or we say mixed condition. Now, third, that is separated boundary condition. So, it means that here one condition is given in entirely at one end point, and other boundary condition is given at the other end point. So, here your L1y is defined only at say alpha y equal to x equal to alpha. So, we say A naught y alpha plus A1 y dash alpha equal to A and d naught y beta plus d1 y dash beta equal to B. So, here your A naught A1 is some non-zero and B naught and B1 are 0. Similarly, in L2y your C naught and C1 is given as 0 and D1 and D naught and D1 are non-zero values. So, here we say that your boundary conditions first boundary condition is defined only at x equal to alpha and the second boundary condition is defined only at the other point, that is x equal to beta. So, your boundary conditions are separated. So, we call these boundary conditions are separated boundary conditions, and here we are assuming that not all a naught a 1 is 0. So, we assume that a naught square plus a 1 square is different from 0, and similarly d naught square plus d 1 square is different from 0 here. Then there is one more very important kind of boundary conditions, that is periodic boundary condition. So, it means that the initial point is the same as final point. So, it means that the value of y given at alpha is same as given at beta. So, y alpha is equal to y beta, and similarly the derivative. So, derivative is the value of derivative at alpha is same as the value given at the point x equal to beta. So, here y alpha equal to y beta and y dash alpha equal to y dash beta is these kind of conditions are known as periodic boundary condition. So, the initial point, the value given at initial point is same as the value given at the final point. So, it means that y alpha equal to y beta and y dash alpha equal to y dash beta. So, these are some important boundary conditions which we need to discuss very often. Now, let us consider one example. So, let us take boundary differential equation, say y double dash plus y dash plus y equal to 0, and here boundary conditions are separated boundary condition, and it is a Dirichlet kind of boundary condition, that is Ly y equal to y of a and L to y is equal to y of b. So, it is the first kind of boundary condition, and it is also a separated boundary condition, and so any solution of this which satisfy the conditions at a and b are simply a solution of this. So, in particular if I take your y a equal to 0 and y b equal to 0, we can say that solution of this satisfying this is a solution of the given y b. So, we simply write it 0. So, it means that any solution which satisfy this and these conditions are known as the solution of this boundary value problem, and in fact this is a homogeneous boundary value problem. Then consider the next example. Here we have a homogeneous boundary value problem. So, y double dash plus E t y dash plus 2 y equal to 0, and t is lying between 0 to 1. Boundary conditions are this y 0 equal to y 1 and y dash 0 equal to y dash 1. If you recall, this is a periodic boundary conditions, and here let us write this y 0 y 1 this as L 1 y equal to y 0 minus y 1, L 2 y as y dash 0 minus y dash 1. So, here L 1 y equal to 0 and L 2 y equal to 0 give you these periodic boundary condition, which is defined like y 0 equal to y 1 and y dash 0 equal to y dash 1. So, we can simply say that if you take any say non-homogeneous boundary value problem, that is Ly equal to sin 2 pi t, or we can say y double dash plus E t y dash plus 2 y equal to sin 2 pi t, along with the boundary condition, that is y 0 equal to y 1 and y dash 0 equal to y dash 1. This will constitute a linear non-homogeneous boundary value problem. So, these are example of some boundary value problem and some boundary conditions. Now, we again define the classification of boundary value problem in terms of linear and non-linear. So, a boundary value problem which is not a linear boundary value problem is called a non-linear boundary value problem, and this is happening because this non-linearity in a boundary value problem may be introduced because of the following thing. The first thing is the differential equation may be non-linear, right. So, here we have two components, one is differential equation, other component is your boundary conditions. So, your non-linearity a boundary value problem is said to be linear if both the equation as well as the conditions are linear, and if any of these two fail, then we call this as a non-linear boundary value problem. So, it may happen due to that differential equation may be non-linear and the given differential equation may be linear, but the boundary condition may not be linear. So, we simply say that non-linear boundary value problem is maybe because of equation may be non-linear or the condition may be non-linear. So, let us consider some example of nonlinear boundary value problem. First problem is y double dash plus mod of y equal to 0. Here t is defined from 0 to pi here. Our boundary condition is y 0 equal to y pi equal to 0. So, these are conditions which are defined in on the boundaries, and if you look at these are very simple boundary conditions, separated boundary conditions. But if you look at the equation contain your modulus y terms. So, it is a nonlinear differential equation. Your boundary conditions are linear, but equation is nonlinear. So, we simply say that it is a nonlinear boundary value problem, and I hope that you already know how to check whether it is a linear or nonlinear boundary value problem. For that, you define operator Ly as this y double dash plus mod of y, and you check that if L of alpha y1 plus beta y2, if it is equal to alpha L of y1 plus beta L of y2, if this holds, then we call it linear, and if this does not hold, we call it nonlinear. And if you check that here it is not holding, so you can check that differential equation is not a linear differential equation. So, we call this problem as nonlinear boundary value problem. Now, look at the next example. Here boundary value problem is y double dash plus 5y equal to e to power t sin t. T is again in some interval, let us say 0 to 1, along with the boundary condition y 0 into y 1 equal to y dash 0 equal to y dash 1. So, here if you look at your boundary conditions are not linear. So, we simply say that your equation is linear, differential equation is linear, but boundary condition is not linear. So, we again call this as a nonlinear boundary value problem. Now, why again we are discussing the boundary value problem different from initial value problem, because we have already discussed the initial value problem, we have discussed the existence in homogeneous theorem and consider several method to find out the solution of initial value problem. But why we are bothering about boundary value problem? So, we can say that the existence and uniqueness results of boundary value problem is in general quite difficult than the theory of initial value problem. For example, take very simple example and try to understand why this theory of existence and uniqueness for boundary value problem is say difficult than the initial value problem. So, first let us take simple example y double dash plus y equal to 0, and take the initial condition y 0 equal to c1 and y dash 0 equal to c2. This is a simple initial value problem, and we know the solution is given as yx equal to c1 cos of x plus c2 sin of x, and you can take any c1 c2 and you can get your solution in a very nice way, and solution is given. But now let us, in place of initial condition, now let us define boundary condition and see that how this nice solution is changed into a difficult solution. So, equation remains the same, that is y double dash plus y equal to 0, but now your boundary conditions are changed. Your boundary conditions are y 0 equal to 0 and y pi equal to some epsilon. So, some value epsilon may not be 0 value, and we can see that it has no solution at all. Though how we can check that it has no solution? So, what we try to do, we try to solve a this equation for a general initial condition. So, we simply say that your yx is equal to, general solution of this differential equation is c1 cos of x plus c2 sin of x, and we want to find out this c1 and c2, but not with the help of initial condition, but with the help of boundary condition. Now, we look at y 0 equal to 0, this forces us to choose c1 equal to 0, right, because if you put x equal to 0, then sin x is 0, so and cos x is 1, so c1 has to be 0. And but if we look at y pi equal to epsilon, then look at here what you have this is epsilon equal to c1, and c1 is 0, so it is c2 sin of pi. Now, sin of pi is simply 0, but here we have a non-zero value, so it means that this has no solution, right. So, simply say that when y of pi is some non-zero value, then it has no solution, right. But suppose you look at this case, that here y double dash plus y equal to 0, y is equal to 0, y pi equal to 0. Now here we have taken the value epsilon, but if you take epsilon maybe any value, may be very small, but still it will have no solution. But if you take epsilon as 0, then we can easily check that it has a infinitely many solution. That is quite say very strange thing, because here we just differ our boundary condition by a little. So this epsilon may be very small quantity, but still in one case we have no solution, but in other case we have infinitely many solution, and you can easily find out the infinitely many solution as here. If you look at, in place of epsilon, if we put 0, then 0 equal to C2 sin pi. Of course this is 0, this is 0, so I can take any value of C2, right. So it means that we have infinitely many choices for this C2, and we can say that our solution is given as yx equal to C sin x, and you can take any value of C, and you take different value, we have a different solution of this. So here we say that we have just changed the boundary condition a little, but we have in place of no solution, now we have infinitely many solutions. So that is very strange for this boundary value problem. Now look at next example, that is y double dash plus y equal to 0, y 0 equal to 0, and y beta equal to epsilon. Here beta is any number between 0 to pi, and you can say that it has a unique solution, and solution is given as yx equal to epsilon sin x upon sin beta. That also you can get it from this. So you can say that y 0 equal to 0 means C1 equal to 0. So it means that now we have yx equal to C2 sin of x, and y beta is equal to epsilon is given. So epsilon is equal to C2 sin of beta. So C2 sin of beta you can get. So C2 is what? Epsilon upon sin of beta. So solution is given as yx equal to epsilon sin x upon sin beta, and this is a unique solution. So it means that if you change your boundary condition a bit, and you have all the cases, that no solution, unique solution, and infinitely solution. So it means that here we have to look at our existence and uniqueness theory in a very careful manner. So now let us start with the simplest possible cases. The simplest possible is the homogeneous equation with homogeneous boundary condition, and we know that a homogeneous boundary value problem has a trivial solution, that is 0 solution. So we say that consider the differential equation this p naught x y double dash plus p 1 x y dash plus p 2 x y equal to 0 with the boundary condition L1 y, which is defined like this. So L1 y is defined as a naught y alpha plus a1 y dash alpha plus b naught y beta plus b1 y dash beta equal to 0. So we can summarize this to write L1 y equal to 0, and similarly this as L2 y equal to 0. So we have a homogeneous differential equation and homogeneous boundary condition, and we already know that 0 solution satisfy this, but we are interested in finding the non-trivial solution. In trivial solution already exists, that is 0 solution. Now how to find out non-trivial solution? So we try to first find out the condition under which we have a non-trivial solution for this homogeneous boundary value problem. So for that, let y1 and y2 be any two linearly independent solution of the differential equation. Then the homogeneous boundary value problem 4 and 5 has only the trivial solution if and only if this term is, this quantity is different from 0. If this quantity is equal to 0, then we may have more than one solution, but in case when this quantity delta is non-zero, then we have only and only trivial solution. So let us prove this. So proof is quite simple. You simply say that your general solution is written as yx equal to c1 y1 x plus c2 y2 x, because it is already given that y1 and y2 are two linearly independent solutions. So general solution you can easily find out. So general solution given that. Now we can find out c1 c2 using the boundary condition. So if you use boundary condition, then L1 of c1 y1 plus c2 y2 is c1 L1 y1 plus c2 L1 y2 equal to 0. Please look at here your boundary condition, which is defined as L1 y and L2 y. This is a linear form, I will say. It means that this is a linear in terms of your y alpha, y dash alpha, y beta and y dash beta. So it means that I can easily check. In fact, I request you to check that L1 y is a L1 y and L2 y are linear in argument, that is y here. How you can check? You look at here. So, let me write it 1 L1 y equal to a naught y alpha plus a1 y dash alpha plus b naught y beta plus b1 y dash beta, and we want to check whether it is linear in terms of y or not. For that you write L1 y alpha y plus beta, alpha is we have already taken. So, let us use some other. So, let us say you say R1 and R2. So, let us say R1 y1 plus R2 y2, and we want to check whether it is R1 L1 of y1 plus R2 L1 of y2. If it is, then we say that L1 is a linear in terms of y, and that you can easily check that it is actually satisfying this. Let me write it here. So, this is what this I am writing as a naught y alpha is R1 y1 plus R2 y2 defined at alpha plus a1 R1 y1 plus R2 y2 dash alpha plus b naught R1 y1 plus R2 y2 defined at beta plus b1 R1 y1 plus R2 y2 dash beta is equal to. Now, this if you simplify it is what here R1 y1 plus R2 y2 given at alpha is what R1 y1 alpha plus R2 y2 alpha. So, we can simplify and we can write it R1, and here we have a1 a naught y1 alpha, that you can easily check. So, this we are taking and here we are taking. So, here we what here a1 y1 dash alpha plus, look at this term, here we have b naught y1 beta plus here we have b1 y1 dash beta plus, look at R2. So, here R2, look at the last term. So, here if you look at this, then we have a naught y2 alpha plus, look at this term. So, it is y2 dash alpha into a1 plus this term, that is b naught y2 beta plus this term, that is b1 y2 dash beta. So, this is what R1, and if you look at this is what L1 in terms of y1 plus R2. Now, look at this, this is what L1 y2. So, we have proved or we have shown that L1 R1 y1 plus R2 y2 is equal to R1 L1 y1 plus R2 L1 y2. So, it means that L1, similarly we can prove that L2 also is linear in terms of y. So, we are going to utilize this. So, here we simply say that L1 of C1 y1 plus C2 y2. Now, using linearity it is what C1 L1 y1 plus C2 L1 y2 equal to 0, and L2 C1 y1 plus C2 y2 is equal to C1 L2 y1 plus C2 L2 y2 equal to 0. Now, to find out a non-trivial solution, we must have that we should have a non-trivial value of C1 and C2. Non-trivial values of C1 C2 means non-zero values of C1 and C2. So, we here we have this and L1. So, we simply say that we will get a non-zero value provided this C1. Let me write this equation, right. So, this is what Ax equal to b kind of thing. So, here we have C1 C2 and it is like this, and here we have what L1 y1, L1 y2, L2 y1, L2 y2, and here we have 0 0. So, we have Ax equal to 0 kind of thing. So, here this will have a only a trivial solution provided that determinant of this coefficient is basically non-zero. So, we say that this system has a only trivial solution provided that determinant is non-zero, right. So, that is the content of this theorem, that this homogeneous boundary value problem will have a trivial solution if and only if this quantity delta is non-zero, determinant of this value is non-zero. So, that is one. So, if it is 0, then we may have more than one solution. In fact, we may have infinitely many solutions. So, that is the content of this corollary, that the homogeneous boundary value problem has an infinite number of non-trivial solution if and only if delta is equal to 0. So, we have just taken the halfway, you have to prove the remaining part. So, we say that if delta that quantity is 0, then we have infinite many solution. If delta is non-zero, then we have only a trivial solution, but it will always have a solution. So, let us consider one example, that is y double dash plus 2y dash plus 2y equal to 0. Boundary condition is given as y 0 equal to 0 and y pi equal to 0. And to find out the solution here, we simply first find out the general solution of this. For finding the general solution of this, we can use we can find out the solution by given method. So, here you can simply say that here solution is given as e to power minus x sin of x, you can call it y1, and y2 as e to power minus x cos of x. That you can simply check that it is what you can write it. Your auxiliary equation is m square plus 2m plus 2 e to power mx equal to 0, and it is m plus 1 whole square plus 1 e to power mx equal to 0. When you put y as e to power mx as a solution here, then you will get this as a solution. So, this quantity has to be 0, and using the boundary condition you can fix it. But if you look at here, I just want to go back again, because here if you look at this is depending on the boundary condition, basically it is not depending on say solutions. Here you take y1 and y2 are any two linearly independent solution, but this delta is depending on the boundary condition rather than a specific initial a specific solution of this boundary value problem. So, it is very much centric about the boundary condition rather than your solutions itself. So, here you can take any two linearly independent solution and you can easily check this. So, let me take solutions as e to power minus x sin x and e to power minus x cos of x, and that you can easily check. So, general solution you can find out y of x equal to c1 e to power minus x sin of x plus c2 e to power minus x cos of x. Now, we have already condition L1 y equal to 0. So, you can look at the delta here. Delta is what? L1. So, let me write it. What is L1 here? L1 y is y. Let me write it here. So, here L1 y is basically y at 0, right, and L2 y is y of pi, and it is given as 0, and yx is already given c1 e to power minus x cos of x plus c2 e to power minus x sin of x. So, we can easily check L1 of y1 is basically what? Y1 is this, y2 is this. Let me see whether I have defined. Okay, so you can easily check your what is L1 y1. So, let me write it, y1 is this, y2 is this. So, L1 y1 is basically what? E to power minus x cos x defined at 0. So, that is going to be what? It is going to be 1 only. Is it okay? Now, L1 of y2 is what? L1 of y2 is going to what? Define this at 0. So, this is going to be 0. Then L2 y1 means this at defined at pi. So, it is e to power minus pi, cos of pi is minus 1. So, it is minus. L2 of y2 is going to be again 0. So, now look at the determinant. Determinants is L1 y1, L1 y2, L2 y1, L2 y2. That determinant we are, this is your delta. So, this L1 y1 is basically 1, L1 y2 is 0, and this is what? E to power minus of e to power pi, and this is 0, and you can see that it is having what? It is 0 basically. So, it means that this delta is coming out to be 0. So, it means that our theory says that it has infinite many number of solution, and you can easily check that your infinite many solution is given by yx equal to c into e to power minus x sin of x. How can you check that? So, this theorem simply says that it has infinite many number of solution. How to find out? that is up to you, means you have a general solution and you have boundary condition, you can easily find out the solution. Let me say that here your condition, your general solution is this, then y 0 equal to 0 means here you simply say that C1 has to be 0 using y 0 equal to 0. Now y pi equal to 0, let us use this and how to see, then this is what C1 is 0 means only C2 is there. So C2 e to the power minus pi here, and sine of pi is simply 0. So 0 equal to C2 into 0, so C2 you can take any value. So let us say k belongs to R. So here we simply say that your solution is C e to the power minus x sine of x, and C is coming from R. So we can say that here we have infinite many solution and given by this, and this we have checked using delta. Here delta is coming out to be 0, and so we have a infinite many solutions. So we have seen that in a homogeneous boundary value problem, when we have a one solution, a trivial solution or a non-trivial solution, infinite number of non-trivial solution. Now let us look at the non-homogeneous boundary value problem with non-homogeneous boundary condition. So the non-homogeneous boundary value problem, p naught x y double dash plus p1 x y dash plus p2 x y equal to R of x, and non-homogeneous boundary condition is given L1 y equal to A and L2 y equal to B. This has a unique solution if and only if the homogeneous boundary value problem with homogeneous boundary conditions has only the trivial solution. So that is why whatever we have discussed is going to be very useful in finding the solution, unique solution for a non-homogeneous boundary value problem. So if we have a homogeneous boundary value problem has a trivial solution, then non-homogeneous boundary value problem will have a unique solution. So let us say how the proof goes. So let us look at y1 and y2 be any two linearly independent solution of the differential equation 4 means your homogeneous part, and zx be a particular solution of non-homogeneous equation, that is this. So zx is a particular solution of this boundary this non-homogeneous boundary value problem, this, and it will satisfy this. So it means that then the general solution of one can be written as yx equal to c1 y1 x plus c2 y2 x plus z of x. So it means that this is a general solution of this along with boundary condition. Now since it satisfies the boundary condition, so we write L1 of c1 y1 plus c2 y2 plus z equal to A, and L2 of c1 y1 plus c2 y2 plus z equal to B, because if okay, so it satisfies this condition because y is a general solution of the non-homogeneous boundary value problem. So if you simplify this, you simply say that since L1 z is equal to A and L2 z equal to B, so this 11 equation number 11 reduced to this C1 L1 y1 plus C2 L2 y2 is equal to 0, and C1 L2 y1 sorry, this is L1 plus C2 L2 y2 equal to 0. And if you remember, this is precisely the term we say that this equal to 0 means this implies that the homogeneous part has a unique trivial solution provided that this delta, which is given as L1 y1 L1 y2 L2 y1 L2 y2, this determinant is non-zero. So if this determinant is non-zero, then you will have C1 equal to C2, we have a trivial solution for homogeneous part. When you put a trivial solution for homogeneous part, then this will simply say that this will cancel and we have yx equal to zx as the only solution. So we say that non-homogeneous system 11 has a unique solution if and only if delta is non-zero, because if delta is non-zero, then we have C1 equal to C2 equal to 0, and we have only solution given as yx equal to z of x. So we can say that this non-homogeneous system has a unique solution if and only if delta is non-zero, and we can say that if and only if the homogeneous system has only the trivial solution, and delta is not equal to 0 is the equivalent to the homogeneous boundary value problem having only the trivial solution. That is what we want to conclude from this equation. So from 11 you can conclude that trivial solution for homogeneous boundary value problem is equivalent to say that we have a unique solution for non-homogeneous boundary value problem with non-homogeneous boundary condition. So, let us take one example based on this. So, let us consider this example. Consider the boundary value problem x square y double dash plus 7 x y dash plus 3 y equal to 0 with the non-homogeneous boundary condition, that is y 1 equal to 1 and y 2 equal to 2. And we can simply say that since it is a Cauchy-Euler's equation, we can easily find out our solution is given in terms of x to power r kind of thing. So, how to for which values of r x to power r is a solution, that we have already discussed, and we can easily see that y x equal to c 1 x to power minus 3 plus root 6 plus c 2 x to power minus 3 minus of root 6 is a general solution of this. So, this I am leaving it to you, that how to find out a general solution of this. Now, let us proceed further, and we want to find out y 1 equal to 1, and if you use the condition y 1 equal to 1, then c 1 plus c 2 equal to 1, and y 2 equal to 2 means c 1 2 to power minus 3 plus root 6 plus c 2 2 to power minus 3 minus root of 6 equal to 1, and we want to find out the c 1 and c 2 for which it has a solution. So, you just look at the value of c 1. C 1 is here you can simply say c 1 as 1 minus c 2, put it back and you can simplify. So, here you can get c 1 as 2 minus 2 to power minus 3 minus root 6 divided by this quantity, and if you simplify, or you simply say that take this term out 2 to power minus 3 common, then you will get that c 1 is 16 minus 2 minus root 6 divided by 2 power root 6 minus 2 to power minus of root 6. Similarly, in c 2 also we take 2 to power minus 3 out, and you will get c 2 as 2 to power root 6 minus 16 upon 2 to power root 6 minus 2 to power minus of root 6. And once we have c 1 and c 2, you can write down the solution, general solution, as this y x equal to this, and since now c 1 and c 2 are particular values, then we can call this as a solution of the initial value problem, and you can say that this is a unique solution of the boundary value problem here. And this we simply say that since we are getting a unique solution because the homogeneous boundary value problem has a trivial solution. How we can check? You put y 1 equal to 0 and y 2 equal to 0, and when you put y 1 equal to 0 and y 2 equal to 0, then we have c 1 plus c 2 equal to 0, and c 1 2 to the power minus 3 plus root 6 plus c 2 2 to the power minus 3 minus root 6 equal to 0. So, here we can easily check, then this is what 1 1 and 2 to the power minus 3 plus root 6 and 2 to the power minus 3 minus of root 6, this is your delta, right. And if you look at the value is going to be what, this delta is not coming out to be, this is coming out to be non-zero value. So, we simply say that since homogeneous boundary value problem has a trivial solution, then non-homogeneous boundary value problem has a unique solution, and we have not only proved that it has a unique solution, but we also have find out the unique solution here. So, with this we conclude our lecture here. In next class we will continue our study of boundary value problem. Thank you for listening us. Thank you.